In other videos, ExOverZero has provided a variation of an NCEES question to solve step by step, so that if you can solve the ExOverZero question, you can solve the NCEES question. This video will work on the step-by-step solution for the actual NCEES question number 27. So first, pause this video and read the question from your copy of the NCEES practice test. Initial critical thought solution elements. 1. What are you solving for? The quality of the steam exiting the vessel. 2. What is the fundamental process? The mixing of two incoming flows, which produces a certain amount of liquid in the single steam flow which is extracted. 3. What are the first considerations to find the solution in connection to the fundamental process? To identify the proportions of the two incoming flows so that the outlet flow is mixed in proper proportions. Also, to identify the properties of the outlet steam flow which determine its quality. 4. Are there key assumptions? That the process is perfectly adiabatic, and because of this, there is no loss of energy or mass. All energy and mass must be accounted for, and nothing simply disappears. What goes in must balance with what comes out. To visualize the process is simple. Two streams flow into an adiabatic chamber. One is relatively cool liquid water, and the other is relatively hot steam. They mix together, and then that mixture flows out. What comes out will obviously have different characteristics than what went in. One entering stream is purely liquid, and one entering stream is purely dry. The exiting stream is partially liquid, and you must determine what proportion of that stream is pure dry vapor. This is what the quality of steam means. It is the unitless ratio of the mass of dry steam vapor to the total combined mass of wet steam in a saturated sample. Found in NCEES Mechanical Reference Handbook, Section 6.1.3, it is mathematically defined as this. So, the quality of steam ranges from 0, which is 100% saturated liquid, to 1, which is 100% saturated vapor. This quality value increases as the enthalpy increases. The flowing fluids are water and steam, so to maintain proportional balances for the flows, you need to focus on the mass flow rates given. This will ensure that everything that goes in will come out in proper proportion. Notice in the NCEES Mechanical Reference Handbook, Section 6.1.1, that the proportional mixing of steam depends on mass flow values and enthalpies. Here is a simple energy-mass balance equation that we will use. Mass flow 1 times enthalpy 1 plus mass flow 2 times enthalpy 2 equals enthalpy 3 times the sum of mass flow 1 and mass flow 2. The question gives you the mass flow rates for all three streams, but the enthalpies must be determined. This can be done by looking them up in the appropriate tables in the NCEES Mechanical Reference Handbook, Section 6.3, Steam Tables. But, though it's easy to say just look them up, it's actually difficult to understand these tables and know if the value you look up is the value you need. So, here is an in-depth explanation of how steam in these tables works, and in this explanation, the two equations so far discussed will be brought together to provide the final solution. A useful way to think about steam is a sort of H2O continuum. From liquid water at one extreme to invisible dry gas at the other extreme. Moving along this continuum represents one single consistent change, a change in enthalpy. Now, assume sea level atmospheric pressure conditions for all of what follows. H2O is in its liquid phase between roughly 32 degrees Fahrenheit and 212 degrees Fahrenheit. In this section of the continuum, a BTU is the amount of heat added to 1 pound of H2O to raise it 1 degree. So you can see from simple subtraction, the enthalpy associated with this section is 212 minus 32 equals 180 BTU per pound. So, if you take H2O at its lowest liquid temperature, that is just above frozen ice, and add 180 BTU per pound, you will bring it to the boil. But remember, this axis represents enthalpy, not temperature. If you add more enthalpy to this boiling water, it will not increase in temperature. The boiling point marks the beginning of the saturation section. Now adding enthalpy to the pound of water in this section will change how much of that pound is liquid water versus how much is dry vapor. That is, how much H2O is evaporated. So, in this section, there will be a portion of the pound of H2O which is liquid and a portion of the pound which is vapor. As enthalpy is added, less and less of the pound of H2O will be liquid, and more will be vapor. Again, adding heat to H2O in this section will not increase its temperature. It will cause more vaporization of H2O. This is a critical concept to understand for the PE. Saturation conditions will be used over and over and over in the exam questions. Saturation is a key concept. At the one extreme end of the saturation region, you've got saturated pure liquid H2O with 0% vapor in it. And at the other extreme is saturated pure 100% vapor. This point is also called dry steam. Whatever H2O is in the pound here is completely invisible. It's not foggy or cloudy. And no amount of liquid condensate is in it. This section spans 970 BTU per pound roughly. This is the exact place that the quality of steam is determined. Within this region, there will be a certain amount of liquid condensate and a certain amount of dry steam vapor. This is where we will look to find our solution for the practice problem. The quality is some ratio of this region. So for instance, if the quality was 0.3, then that means it is 30% of the 970 span. Beyond roughly 1,150 BTU per pound, any enthalpy added to the pound of H2O will again begin to increase the temperature, like the liquid section. This is the superheated section. Of the 3 enthalpy values discussed, these 2 represent amounts on the actual enthalpy line, while this third one represents the difference between the 2. This is called enthalpy for saturated liquid, H sub F. This is called enthalpy of saturated vapor, H sub G. And this is called latent heat of vaporization, H sub Fg. Values for these enthalpies can be found in the NCEES Mechanical Reference Handbook in section 6.3.1 or 6.3.2. Values in the superheated region are found in section 6.3.3. But it's not so simple. You should remember from your early physics and chemistry classes, water boils at different temperatures depending on pressure. So, the enthalpy requires an established pressure for analysis. If you change the pressure, these values change. Now add a y-axis for pressure on the continuum, and this becomes the skeleton of a pressure enthalpy graph. Showing something visual like this makes it convenient to represent an infinite amount of points. But if you are to make a table which is finite, then there must be a selected group of values from the infinite possibilities. This is why tables 6.3.1 and 6.3.2 in the reference handbook are titled the way they are. Obviously, saturation, temperature, and pressure are priorities. But in what way? For the temperature table, priority 1 is liquid at a given temperature has only one enthalpy value. Priority 2 is saturation of the liquid at that enthalpy has only one pressure. So, 1. 60-degree liquid water has an enthalpy of roughly 28. 2. If this liquid were saturated, then it would be at a pressure of 0.26. Notice how you can check priority 1 with what was stated earlier regarding the sensible heat region of the continuum. Remember the subtraction of temperatures based on the definition of BTUs? That is, 212 minus 32 equals 180 BTU per pound. Substitute that for the 60 degrees in the problem, and you get 60 minus 32 equals 28 BTU per pound. Remember, this is only valid for sea level pressure. The pressure table says, priority 1, liquid at a given pressure is only saturated at 1 enthalpy. Priority 2, saturated liquid at that enthalpy has only one temperature. So, 1. 14.696 psi liquid water becomes saturated at an enthalpy of roughly 180. 2. If liquid were to have this enthalpy, then it would be at a temperature of 212 degrees. Notice that at atmospheric pressure, water with an enthalpy of roughly 180 boils. That is, it enters the saturation region. And water boils at 212 degrees. Use the temperature table to find which enthalpy. Use the pressure table to find where saturation. For the superheated steam tables found in the NCEES Mechanical Reference Handbook, section 6.3.3, things are much easier to understand. The only place saturation data is given is in the heading of each table. It is the lowest temperature value for the given table. Superheated steam is H2O beyond saturation. This saturation temperature is the jumping-off point of the table, essentially saying all values are beyond this point. Things are further simplified by the combining of pressure and temperature data into one table. So start by finding the pressure. Then look up the temperature in the right column, and you've got the pertinent data in a row. Simple. Now use the variables given in the NCEES practice problem and the knowledge of the tables. Table 6.3.1 gives the enthalpy of saturated liquid water, H sub F, at 60 degrees Fahrenheit as 28.08 BTU per pound's mass. The fact that the liquid in the question is not saturated at atmospheric pressure doesn't matter. Priority 2 for the temperature table can be ignored. It doesn't matter if the liquid is saturated. Table 6.3.3 gives the enthalpy for superheated steam at atmospheric pressure when it is 600 degrees Fahrenheit as 1,335.3 BTU per pound mass. Now use the energy-mass balancing equation discussed earlier, found in the NCEES Mechanical Reference Handbook, section 6.1.1, populated with the relevant data. Let mass flow 1 be the water, and mass flow 2 be the steam. 100 pounds mass per minute times 28.08 BTU per pound mass plus 100 pounds mass per minute times 1,335.3 BTUs per pound mass is equal to the enthalpy mix times 100 pound mass per minute plus 100 pound mass per minute. Solve for the enthalpy mix, which is 681.64 BTU per pound mass. Because determining the quality of steam is the same as determining where in the saturation region the given enthalpy is, find where the saturation region is for atmospheric pressure. This is in Table 6.3.2. At 14.696 psi, the saturation region starts at 180.18 BTU per pound's mass, spans 970.07 BTU per pound's mass, and ends at 1,150.25 BTU per pound's mass. So, the first 180.18 BTU per pound's mass is only for the liquid phase and has nothing to do with the saturation region. And because it has nothing to do with the saturation region, it has nothing to do with the quality of the steam. It is the amount of enthalpy that just gets you to the saturation region. So take that away from the total enthalpy mix, which leaves 501.46 BTU per pound for the mixed steam within the saturation region. The span of the saturation region is 970.07 BTU per pound's mass. And as already discussed, the quality of the steam will be some ratio of that span. Set up a simple equation derived from only critical thought about the continuum. Sum ratio x times 970.07 equals 501.46. So, x equals 0.52. To get good at questions like this, study ASHRAE HVAC Systems and Equipment, Chapter 11, Steam Systems, Section 2, Fundamentals. In the ExOverZero practice tests, do problems Test 1, number 26, Test 2, number 28, Test 3, number 29, and Test 4, number 29. These contain extremely valuable variations of the fundamental concepts and equations used in the NCEES practice problem number 27. These problems are not mere repetitions. They expand and deepen your knowledge of this particular subject within the context of practical PE-style problems.